So in chapter 3, we introduced some more advanced solving techniques, including the idea of looking inside, rewriting chunks of the equation, undoing operations, and fraction busters. And these three questions kind of illustrate all of those. One problem. I mean, some of the problems can actually use multiple techniques. So let's look at each one of these. When I look at A, I see that I have some fractions, and I know that I can bust those up but by multiplying every single term on both sides by the same value. And I can do this in one step for this problem by multiplying both sides by 5, or I can do it in multiple steps. Oh no, in one step by multiplying both sides by 10. But I could also do it in multiple steps by multiplying by 5 and then by 2. I'm going to go ahead and choose to do it in a single step. That's bust up all the fractions by multiplying everything by factors of 5 and 2. So I'm going to show that I'm doing this across the entire equation, all the terms, and I'm going to be multiplying every single term by factors of 5 and 2. Now, there are exactly 4 terms that I need to do this to. There's this first term and a second term on the left side, and there's a first term and a second term on the right side. So all of those need to get multiplied by 5 times 2. Another thing that's helpful is when we look at numerators and we see that there's multiple terms within a numerator, it's nice to place parentheses around just to remind us that whatever we multiply that term by, we really need to distribute that at the end, right? So if there's something that has to go across, it has to go across those 2 terms within that fraction. So visually, I think it's nice to write this out at least one step. So I've got 3x plus 2, and then I'm going to be multiplying that times 5 times 2, all of it over 5, and then plus the x that I have times a 5 times a 2, and all of that over 2, and that's going to equal this x times 5 times 2 plus the 5, and then let me write one more, times a 5 times a 2. So if you look closely, you can see, yes, every single one of these terms, this term, this term, this term, and this term, picked up factors of 5 and 2. This is important to point out to yourself because remember, it's a property of the equality I'm using. What I'm using is the fact that if I have equal things, right, if these things are truly equal to each other and I multiply by equal things, then I get equal things. So I'm using this multiplication property of equality. Now, once I've done that, I can say, well, look, this forms a giant 1. I clearly have a factor of 5 over 5, so that's gone. And then here I have another 1 in the form of a 2 over a 2. So now I can rewrite this with no fractions at all. So I can write that this is a 3x plus 2 multiplied by a 2 plus, I'll just rewrite this as 5x, and that equals 10x, and then plus the number 50. Okay, no fractions at all, did it in one step. Rewrite using the distributive property, this becomes 6 times x plus 4 plus 5x equals 10x plus 50. There are some like terms over here. 6 and 5 is 11x, so I'll write this as 11 times x plus 4 equals 10x plus 50. If I take away 10x from each side, that's going to give me a single x over here. X plus 4 is 50. And then if I subtract 4 from both sides, we get that x is the number 46. 46. So x is 46. Definitely worth grabbing your calculator and practicing plugging in 46 to all places where you see x. But when you do that here, here, and here, you do end up getting that 51 is indeed equal to 51. But it's an important exercise to just convince yourself that you can do that. Let's move on to part B. For B, you see that I have an exponential equation. I know that it is that because my variable is in the exponent, and I need to solve for x. The only technique we have this year is to just rewrite this so that our bases are the same. And when I look at the fraction of 1/3, right, and I look at the number 9, I'm immediately thinking a base of 3 is probably where I want to go. So it's helpful for me to write powers of 3 off on the left. So 3 to the first, 3 to the second, 3 to the third, but then also go the opposite direction, 3 to the 0 power, 3 to the negative first, 3 to the negative second. 3 to the first is 3, right? 3 to the second is 9. This is 27, but I don't think I need that. 3 to the 0 power is the number 1. Anything to the 0 power is 1. And I can see that inductively by the fact that I'm taking 27, divide by 3 is 9, divide by 3 is 3, 3 divided by 3 is 1, and then 1 divided by 3 is 1/3, and then 1 divided by another 3, right, would be 1/9. So we can see each of these, and it's a nice reminder of what negative exponents are. The two that are important to me is this 3 to the negative 1 and this 3 to the second power. So I probably am going to go, in fact, I am going to go there. I know that 3 to the negative 1 is the same thing as 1/3. So that's what I'm going to rewrite that part as. And I know that the number 9 is the same thing as 3 squared. So this is me rewriting it. I'm replacing 1/3 and I'm replacing 9 with things that are equivalent to 1/3 and 9. For 1/3, I'm going to write 3 to the negative first power, and I'm going to raise that to the 3x plus 1. On the other side of that, I'm going to replace 9 with 3 to the second power, and that's getting raised to the x minus 2 power. So I'm not quite there yet because I have this situation where I have a power raised to a power. And for me to raise this power of negative 1 to the 3x plus 1 power, or this power of 2 to the power of x minus 2 power, I have to multiply these things. So when I multiply negative 1 times the quantity 3x minus 1, I get 3 raised to the negative 3x minus 1 power. And on the other side, I get 3 raised to the 2x minus 4 power. At this point, I can see that my bases are the same. They're both equal to 3. And this exponent, right, has to equal this exponent if these expressions are truly equal to each other. So that's how we finish this off. We just set the exponent from our left equal to the exponent on the right because this has to be true. If I add 3x to both sides, I can get negative 1 is 5x minus 4. If I add 4 to both sides, negative 1 plus 4 would be a 3 equals 5x. And then finally, if I divide both sides by 5, division property of equality, I get 3/5 is what x was, or I can write down below that x is 3/5. So that is my answer to part B. And if I plug 3/5 into the left and right hand side, I really will get two values that are identical to each other. All right, and then the last part we have was an example of the other technique we talked about, looking inside. Looking in the square root, looking inside of that is problematic because it's not isolated here. So if I were to subtract 6 from both sides, this would become the square root of x plus 1 equals the number 9. Okay. Now that I've got that, right, I can look inside. I can say, look, this thing right here, the square root of that value is producing an answer of 9. So the only way that can be true is if that was 9 squared or if it was 81, right? So this expression 4x plus 1 must be the number 81. Now I want to caution you because some of you looked at this and you thought you could get rid of the square root by squaring both sides as it was originally written. And the problem comes up when you think that you're squaring this expression and you claim that that's just 4x plus 1 plus 36. It's not. That's not what you get when you square it, and it's because you're multiplying that thing by itself. If you think about an area model, you might be able to convince yourself that that's not what this is equal to. A better thing than dealing with that is just use the subtraction property of equality, and now you can say what does that thing inside have to be? It has to be the number 81, because when I square the 9, right, I get an answer of 81. The square root of the 81 would be 9. So now that I know that this thing inside absolutely must be the number 81, I just set it equal to 81, and then I solve for x. So if it has to equal 81, then truly 4x has to be the number 80. And if I divide both sides by 4, I get that x is the number 20. And I can check this answer pretty quickly by just plugging in the 20 here. 4 times 20 is 80. 80 plus 1 is the number not is 80 plus 1 is 81. The square root of 81 is 9, and yes, 9 plus 6 is 15. So this answer works. Other answers do not.